So, good morning. Um, I guess this is the last class we have on Friday. Just to remind you, next Friday we don't have any more classes. Okay, because we have exam on the Thursday night. So you discuss this. We don't have to meet here. Because we'll meet on the Thursday night for the exam. So that means that next week we will be doing review and look over the past year paper. So take your time to work on it during the weekend. So it will be next Wednesday. We are going to do that. And this class is going to be, we'll finish the material on regression. Okay, if you time, we are open up for the Q&A, but I guess it will be almost time we are over. Okay. So so let's see. Okay. Let's see how we are going to finish this one. But let us review everything for this topic because we're almost done. We just left a few stuff here. Okay. And hopefully it will be clear to you. Okay. So regression, by construction, by definition, it means basically try to understand how two numeric variable are related, right? So basically, you have some people, we observe their education and income. We try to see if there's a relationship between them, right? A lot of things we want to study how things are related, right? And then when we study the concepts are connected. And it's an idea that extended from ANOVA, right? ANOVA is trying to study how different groups may have different mean, right? And now the grouping in the ANOVA has no meaning, but now regression, we are trying to say different group. Actually, the grouping is a meaningful idea, right? The grouping is actually now is X numeric variables. And the data we have is just X1, Y1 up to Xn, Yn, and each individual would be represented by a dot in the 2D scatter plot. Okay? And the idea is just to have a line that try to represent the data, right? So that serve two purpose. One is reduce the data to something is easily manageable, right? To a two number, which is the slope and intercept, right? Just we reduce a lot of data point into two number, right? Just what you see in this picture, right, is regression, right? Just basically collapse a lot of data information into a model that only have two numbers, right? It's like simplifying or condense our knowledge, right, into a line. And second, not just condensing, is also generalizing the knowledge from data point to the value that we don't have data on, right? Because data just represent finite number of points, but a line is infinite number of points, so it's many, many whatever, right? So it's just like those you don't have data on, then you still make it work. So that is the idea. Now, the very earliest attempt to draw a line is called the least square method. That is minimizing the sum of the vertical distances between the point and line. So represented in this graph, all the square distance of the the blue line and the red line, the square distance. You try to minimize, you will find one. And because of the square, this line must be unique, okay? Because of this is sum of square. And if you look carefully, what are you minimizing using the terminology? Turn out to be is minimizing the SSE, okay, which we will see later. And what I meant by SSE is this guy, right? This later you see this guy, also known as SSE. Later you will see But of course, in this one, we don't call it this name, but they're the same thing. So it's minimizing the sum of the vertical distances. And if you learn multivariate calculus, I mean the second course of calculus, you know how to find this A and B, right? Basically just moving the intercept and the slope to minimize this guy. And turn out that the equation is this one, okay? And the math behind is too complicated to explain, but we do notice the first equation tells us that the line must pass through the center of data, x bar, y bar, right? So that means that the baseline must go in through the center, right? Represented by this diagram, right? You have an x bar. X bar is the one that in the middle x, right? Go left and right from x bar, we're same. Same idea for y bar. If you go up or down, the same distance, okay? And the line must pass through this center, okay? What does the second equation B means? As you can see here, B is a fraction where the numerator is covariance and denominator variance. So that means that B is directly proportional to the covariance and inversely proportional variance. Of course, why this exactly form, you need the math, but we can make sense of this by looking at the graph. You can easily see that if you have positive covariance, you should expect the line to be positively sloped. And if you have zero covariance, then naturally expect the slope will be zero. Similarly, if you have a negative covariance, you should expect the line to be drawn to best fit the point to be negative slope, right? So that would be the main idea. And we have some more in C to, if you double the variance, you would decrease the B. If you double the X, then you will halve the B because of the formula. And you increase Y by 1, then you doesn't affect B, but you will increase A. So everything would do as you would think, right? So it shouldn't be something a big concern to you. So we know when we have data, when we try to run this regression, of course, we can do from scratch. But as I told you, our class is not computational. So you just need to, I just showed you the formula, right? But you do remember how we derived that from Excel is due to slope and intercept, right? This is the formula to derive that, okay? Of course, I showed you the calculation here because I want to let you know how we do it, right? From the first principle. But in practice, right, you just use the function slope or intercept if you want to derive them. Of course, you'll be doing Excel add-in, just everything will done just by one thing, but that's the idea. Okay, the next is once we know how to fit the line, and it's still only the regime of math, right? So we use calculus. So we didn't actually use anything we learned in this class. So we really want to do more, okay? And when we say study y and x, right, we say how x relate to y, but we do know that in the world it's not so simple, right? Not just x cos y or x relate to y, but there are many, many things as well. And to recognize this, we'll use this kind of model is x and y are related, okay, in the alpha and beta parameter, but there's something that is not captured in your model or not measured from the data, and they are referred to as error. Okay, error is things that is not captured in your model. Okay, of course, if they're not captured in model, you should expect they're not very important in the sense that they satisfy the third and the fourth assumption. such that their mean on average are zero. The variance are the constant for each individual, and different individual do not have any non-zero covariance. Okay, so that means that they are not very important, right? You can simply ignore the random term, their noises. Okay, so in that case, for example, we study X is the education and Y is income, and what is epsilon? The errors are possibly, maybe, how well you do interview, how good you do in the sport, how well we do in piano, right? Because piano can affect income. Suppose the boss like music and then you know how to play piano, the boss may give you a little bit rise. Or the boss like to drink wine, then you happen to know how to find a good wine, then you get a increase, right? Or some boss hate people drink wine, then you know why, then they don't increase your salary, right? So on and so forth, right? It's more or less random, right? So that's the idea. So epsilon is something random. Of course, if you omit something that is important, of course you run the wrong model, right? But in this class we don't have this issue, so we always have no problem with that. But the main thing here is the second assumption, which X is non-random, and because X is non-random, and only random thing in this model is not observe the epsilon, the error. Okay, and that means that there's another thing is also a random variable is the Y, right? Because X is non-random, alpha and beta are just numbers. Okay, just don't know the number, but they're numbers. Sometimes called parameter of the model, right? And epsilon are random variable. Okay, so that's why Y is random variable. Okay. So what does this four assumption bias? Okay, if you are willing to make these four assumptions, okay, of course the most important one is the first assumption, right? But anyway, you're willing to make these four assumptions, then the minimizing the sum of the vertical distance, what we call the least square method, okay, and actually is an unbiased estimator, okay, of alpha and beta, right? And do note that here the A and B are random variable. Why? Do note that we go back to this equation of A and B, right? X are non-random, but Y are random. Why? Because Y would depends on the epsilon, right? And if you don't like the idea, epsilon is the unknown factor, you can say this sampling is sample error, right? Because depend on who you talk to, right? Because there are some people, right? In the world is very different, right? So that's why you have depends on who you talk to. There's a random variable. Okay, so just to make it more clear, that would be the idea, right? So the idea is following, right? So you have a data X and Y, and then you can represent the data by some scatter plot. So the data point, the dot, are the data you have, right? Maybe I forget about data first. Okay, I should talk about data. I should talk about this, how they are related, right? So if you believe that the X and Y related in this way, right? So this is your model, right? So if there's no uncertain factor, right? If there's no uncertainty, right? So that would be, if you call every time you call X, Y will be all along this line, right? So that would be perfect world where epsilon is gone, right? But we know the world is not so perfect, right? Every time you have the data, right? Even they have the same X, right? Most likely it's here, right? But sometimes it's here, sometimes it's here, sometimes it's here, sometimes here, right? And what are these? Why they're different, right? It's called epsilon, right? Of course, different observation of different epsilon, right? This is called error, right? This is called error. Okay, you observe this, right? If your data point is here, then you may observe here, right? But you can observe anything, right? Anything can be happen, right? And we assume the variance is same no matter which x, right? So why we said the A and B's are random variable, right? Because you may say, let me make another one as well, right? So you may end up, when you run the regression, your data is somewhere, say, like this one, this one, this one, right? In that case, we run the regression, will be somewhere here. Maybe somewhere here, yeah, maybe somewhere here. Okay, this is your regression line. And run this regression, this will be your A, and this will be your B, right? And of course, you may not need this point. Maybe you end up in this 3 point here, right? And if you do so, you run the regression, you may end up in this one, right? So you will end up in this B and this A, right? So you end up in different B's and different A, right? So that means that A is a random variable and B is random variable, right? Before you collect data. Of course, once you collect data, A and B are no longer random variable. But in principle, depends on the data you got. Oh, of course, depends on what the errors they are. Okay, you can end up in different A and different B's. Okay, but if you're willing to accept this for assumption, uh, is unbiased, which means that you run one set of regression, you get like one set of A and B, and other set you have A and B, and you have many A's and B. If you run many regression, average of this A will give you the right alpha. Average of this B will give you the right beta. That's called unbiased. Okay, so that's why we have a trust in this system, because the algorithm tell us that if you repeat this many times enough, we'll uncover the truth. Okay, so that is called unbiased. Okay, but this hope you understand A and B are random variable. Okay, the thing that we got is a random variable. So that's why we have later you see with variance, right? For this, and then because A and B are random variable, that's why you can tell us we can do hypothesis testing on alpha and beta. We can do interval estimate for alpha and beta. Okay, so that's the main idea behind. So let us get back to the slide. Okay, and we have interpretation of this will be when we run this model. Once we find A and B, then this is what we say, right? This is the estimated model, and A would be our expected value of Y on average, Y if X is 0, and B will be average value of increase in Y when X increased by 1. Okay. And here, one thing you will see, right, is we talk about residual. Why is the case? Look at the graph again, just to make sure you get the idea. Here is epsilon there, right? And in this model, if you think the epsilon, right, have the variance called sigma, right? The variance called sigma. Maybe use the green color. Sigma square. Okay. The variance epsilon is sigma square. And you can see the larger the sigma square, right? And you have where the trust on your model will be less, right? Because if sigma is very small, then you expect X and Y are related very strongly, right? If sigma square are large, then actually then your model may not be that good, right? Because you have a lot of things that actually not in the model, not captured by your model. So that means that we want to know the size of sigma square. Okay. Okay. Of course, we want to estimate that. Okay. And of course, later you will see we will use the MSC to estimate that. okay, the MSE, okay, which, or we call the user residual, okay? And why this is important? Because the size of, you can see the size of sigma square will determine how big the variance of your estimate A, okay? And also how big the estimate of B, right? If you have larger sigma, then you have a bigger range for alpha, so a bigger range for A and bigger range for B, right? If you have a lot of variation in data, right? Then your A and B, the possible range will be higher, okay? And that affect our estimation and also affect our hypothesis testing, okay? So that's why we need to have some way to guess what will be the epsilon, okay? How we estimate the epsilon is based on our regression data, okay? Say, focus on the black dots, okay? And the back equation, right? So this will be, we call y hat, right? A plus B, right? So this is our estimated model. Okay, forget about the light blue one, okay? Just the black one. So this is our model. And because we never see the green error thing, so to estimate that, we will do what we call the sample counterpart, okay? This is called the difference between the data point to this is called residual. That's called E, okay? Residual. Okay. So epsilon, right, is the data minus the line, the line and then square, right? So you can do the same, right? We can do the same calculation, which is called S square, right? Will be just this EI square. Okay. And for EI is defined as YI minus YI hat, right? So it just the data point minus a line and take a square, right? And if you notice this, right? This guy is SSE, right? It's actually, if you run the regression least square method, this is what we're minimizing, right? Minimizing the point to the line, right? That's what minimizing, right? And of course, this is a name as well. This sometimes is referred to MSE. Okay. And of course, if you do the square root of this guy, right, which is this guy, right? This is RMSE. Okay. And this is also known as standard error of estimate, okay, or sometimes called error of regression. And this is, okay, the very important thing, right? And then you learn Excel. This is Excel is STEXY, right? So this is the equation, right? And S, or remember what we're doing. This guy is to estimate sigma square, okay? S square, we calculate that is to estimate sigma square. And why we do that? Because, and some of you would ask why divide n minus 2 and not n minus 1 or n, because there's a complicated calculation to show that this is the unbiased estimator. Have to divide n minus 2. And you can see, even though I don't bother to put in the slide, because the proof is so complicated. I mean, you have probably take 1 A4 paper to do the whole proof, maybe more than 1 A4 paper, but I think it's too much for you to consume. Okay, so I just don't put the proof here, but I already said in the slide, this is the thing. Okay, so you need to know this is the formula. Okay, and what we're doing, we are trying to see how good fit the model is. Okay, and some of you, if you learn machine learning class future, you will see actually many of the way you do machine learning is trying to minimize this kind of measure. Okay, you can pick pick the MSE or RMSE. This is the two measure that either of them the same, right? You pick one of them to minimize. Suppose you run a random forest, you run any machine learning algorithm, you will do that. Or you go regression tree, you do a lot of many things. This is the thing that you will be doing is to minimize how your model perform compared to your data. Some of the vertical distance is a very standard thing you would see. Okay, you can see a lot of Python package. You can do it as well. Okay, and now once you have S, okay, we know this sigma square, and then we would know how A and B is different. That is a thing we did in last class, I guess. Okay, so once we, oh sorry, you want to take a picture? I can see that. Anyway, the worst case scenario is go back to the record the lecture and take a picture. It's there, it will be there already there. So once you do the calculation, okay, it's a variance, right? And just to remember this STUY so that would be, so as I told you, this is unbiased, okay? And after that, we are going to tell you how to do hypothesis testing and interval estimate for A and B, right? Because this is what I want to illustrate that whenever you estimate model in statistics, you do two things. One is you estimate it, which is the come of the point estimate. And then you do two things. First, you have to do hypothesis testing, right? And see if the parameter is meaningful, right? That is it different from zero, right? If it's zero, then basically useless. Okay. The second, if not zero, and try to see how good they are, right? You want to look at the 95 confidence interval and have some idea what the value is, right? Same as what you see when you see typhoon, right? And you see whether typhoon is going to hit Hong Kong, right? If not, then just forget about it, right? No matter how strong it is, right? And you see, if you see typhoon is coming, the signal one is coming, and you want to see how likely it's coming, look at the typhoon is going to hit Hong Kong or not, right? And look at, is it 95% you hit or not, right? Then you will see, right, the same idea, okay? So, with intercept, is this variance A and this formula, right? I think I explained why last time, why this is right? And the idea is if you have more variance, as we said, then you have A will be less accurate, right? And if more data, then A will be much more accurate, right? And if your data is, maybe I just write down here, right? Because make it more clear, right? So this first item is saying that if your original variance is very large, then A will be very large as well. Here it means when n, the more n, then you should have less variation, right? So this one implies that when your x is actually far away from zero, of course, you will have more variation, right? I think I draw the graph already. Maybe I just show this graph in case you would want to see, okay? But I think I have that many times already, so you can imagine this is your data compared to different cases, okay? And your data generating process is like this, right? So this is y equal to alpha plus beta, the same thing. Okay. But if your data is in fact, this one is very close to x, okay? And the other case is very far away, okay? Why the case on the left have smaller variance on A than the case on the right? So let's see. Let's use the green on the, maybe I use green, right? To make description easier. So why the green one would have a lower variance, okay? Let's try to draw a diagram. Okay? If you draw it, this may be the line, maybe. So the green one, if you, maybe you get, suppose you get this data, this is your data, right? Then what is your best fit line? Will be something like this. Okay. And if the data is like this, okay, your line will be somewhere like that. Okay. What happened in the other case? If your data is here, right, your line will be somewhere here. Okay. And if the data is again like what I'm doing, right, your line to be drawn with somewhere like this. Okay. So here you will see the possible range, right? For A, it's increased, right? Suppose you are increasing this one, right? So your data is actually much further away from zero, which of course includes the sum of this square, right? In this case, this will be more. Okay, is that clear? So I hope I convince you that this is the case. Okay, but of course, ultimately we are on the math, but this is the formula, right? Because once you assume the bell curve of the error, then A also bell curve. Okay, once we know the intercept bell curve, okay, then we can do a lot of things because we know how to handle bell curve, right? For the bell curve, once we know the mean and variance, we can do a lot of stuff. Okay, the only troublesome for this one is we don't know sigma square, but that's not an issue. We can use the S, okay, to do our job. Okay, S of job. And this represent by S of A. Okay. So once we have that, then because of normal, then we can do hypothesis testing on alpha, right? We want to see alpha is same as 0 or not, okay? And just to remind you, what we are doing is a bell curve, right? And this is alpha here. The variance is sigma A square, right? And what sigma A square? Sigma A square will be sigma square over root n, right? If you look at the formula, right? So this is the formula, but the troublesome point of this is we don't really know the sigma, right? So you know the bell curve, we can replace the sigma by S, right? In that case, you can look at the T, right? That's what you do, right? You look at it instead, look at the T. Tn minus 2. This becomes 0, right? And right, so how can you convert to T here, right? Just basically any value, right? You would subtract it from the alpha, right? In this case, you assume 0, right? Subtract from 0. So this is A, right? The value of A here. And it will be A, right? Divided by S of A, right? S of A will be just you replace sigma by S and you just take square root, right? S of A, just to remind you, will be just S over root N, right? And the square root, sum of the X square, sum of X minus X bar square. Okay? And just to remind you what's the S, right? S is this guy, right? S with the square root of sum of the EI square and N minus 2, right? So that is, of course, you calculate your regression, calculate the error, and calculate this, but this one is STUYX, right? And then once you do this and plug this in, and you can calculate all that, okay? Although you can see the calculation is very convoluted, very complicated, but just to remind you that we are never doing this calculation by hand, right? Although in the slide I show you how to do it by hand, but this automatically output from the Excel, right, or any software, right? The idea will be just simply checking the p-value, right? Remember, you want to see from 0, we'll be asking, right? If this A far away enough from the middle, which is 0, such that we can say reject from 0, right? And very often it's two-tail test, right? Two-side test. So you calculate area, the p-value times 2, right? This is the standard thing you would look at any software. It's by default is two-tail test. Okay. So this is the thing, right? And I think we already tell you because of this is a bell curve, right? That's how you can extend the interval estimator, right? Just A and plus this value, right? And times this, right? We know how to do that already, right? So that with the formula, right? This is, remember, this is the same as what we see many times before, right? If you still remember, right? Okay. And now with this one, because this is the variance, there's SD of this guy, right? And this SD of this guy, the same thing. Okay, so there's no new formula here, the same formula, right? But this is the SD of this guy. So this SD of this guy, same formula. So there's no new formula at all. Let's say same formula, right? But we have a new way to figure out what is the SD of the A, which is S of A. Okay, because remember what is this guy is S of X, right? Okay. So once we have that, then we're done, right? So that's how look at the intercepts. Okay. So before the break, I want to show you again, focus you on this one, right? And what we have reviewed, right? This is our A, and this is our B, right? And we just show you that this is S of A, right? And this T stat, right, is simply the T is just A over SA, right? Okay, this is the value in the T table, right? T in the T distribution, right? Tn minus 2 here, right? This is 0, and you get this number, right? This is the T. And you calculate this p-value. This is a two-side test. This p-value is 17%, so it's not small enough. Okay, so you can't reject, right? Because remember what it's doing, this p-value is testing this, right? X0. is alpha equal to 0. X1 is alpha not equal to 0, right? So it's P is big. So you are not rejecting this, so you keep this guy, right? And what is the remaining column, right? So the last two columns are the same B.B.A, so but just focus on these two, right? So this will be just the confidence interval, right? Estimated result, right? So this one will be just A plus minus T n minus 1 alpha over 2 as A, right? So we have seen that, right? So this tells you that although we figure out A is 3.9, it can go as low as -3 and go as big as 10, right? So that means that this A is cannot say different from 0, okay? So by convention, if this is not different from 0, we'll treat it as useless, okay? So A by default, we'll think is 0, okay? That means that we'll say usually when X is 0, we'll say Y is 0, okay? In this particular case, because although the actual one is 3.9, but we'll not trust this result enough, okay? Is that okay? So after the break, we'll talk about, again, for this B column, and we'll finish. You see everything we are done from this slide, because this slide is the single most important thing for this topic, right? Because you understand every aspect of this one, then probably you understand the whole chapter, right? Because the main thing is the whole thing, right? They summarized by this Excel output. Of course, you will say if you don't use Excel, you use other software, same thing, okay? You see very similar. Use Python, use R, you can see almost the same output, okay? Of course, R will have a little bit more information, and Python is furthermore. But this is the most important thing. I don't see many of time you use more than that, okay? So I guess if there's no, is there a question? Okay. With no question, then as usual, let me open the U reply. Okay. And we will see your reply from us. So now it's 10:20. So we will resume at 10 34. Okay. And because this is almost my last lecture for us, okay, because next class we'll do just review and Q&A, right? And also we are say goodbye to this room. So we're celebrating this end, right? By sharing some snacks with you, okay? I'll see you in 15 minutes later. Okay, let's see how we're doing. What's meaning of x0? I think that's the last slide in our class. X0 means that particular x, just some x value. So nothing but just some value there. Okay. Uh, because I think he's asking this slide is asking this x equal to x0. X0 just some number 1, 2, 3, 4, 5. But I just don't put the numbers in. Okay, we'll talk about this at the very last minute of our today. Which topic is most important for exam? Uh, well, I can't say which one because everything is in exam. I think every topic we have at least one question in exam. So hard to say it. But that's what I can say because I don't know what is more important. But if you have asked me, I think our class you would to know estimation, hypothesis testing would be the two important things, right? Because regression and ANOVA is just application. So if you know very well how to do hypothesis testing and estimation, which you already should know it from your assignment, then it should be fine. We will discuss this in the next class. Okay. Answer will not be given in written form, but I will talk about that in the class. But I will not release the written. You can write down, but I'm not going to send out the thing because it's open book. It looks bad if you bring the answer and try to do thing. I mean, I don't think that's a good learning experience. Okay. Is it almost the same? I don't know, but I would not say, well, why maybe I say there will not be too big variance, but there will be some variation, of course. Okay. Don't expect the same thing, right? There's some variation, but there's not too much variation because you can see the past paper is indeed including the most important thing in the course, right? So already the main thing we talk. So maybe we'll change the way we ask or change the stuff, but it should be not too surprising, right? Because the important thing for the course should be not this different from the other year. Yeah, so I hope you are done with the statistics and no need to suffer anymore. Okay, you enter into life there will be no statistics in your future hopefully after next Thursday. Excel add-in, as I said, I don't ask exactly how you operate Excel add-in, but you need to read the Excel add-in. That is something I would need to ask you to do it. Okay, I will not ask you which button to push out the Excel add-in, but Excel add-in output will be needed because that is the output, right? Is the thing that we learn in the class, right? So, I hope I answer your question. Yeah, we don't ask you add-in. Just basically, we give you output, and you have to make decision based on that. Okay. For example, you can see our past year paper. That would be the idea behind. Sleepy, yes, I can see. So p-value, for example, there's no way, except there's z normal distribution, you can find the p-value, right? But if you look at the t, look at the f, you really can't do it. Okay. So you can bring any table that you need. Okay. Standard normal, then you have to bring your own. And for T, you also bring your own, but also I would properly provide for some questions. Okay. And you may use the one I give. That should be sufficient. But if not, then you can bring your own if you worry. And if I don't ask the p-value, if I've asked the p-value, you can just use the Excel formula, right? And it's fine, right? And that would be done to give me the value based on that. Okay, you can tell me if this value is more than 0.5, 0.05, what you do. If more than that, what you do. Right, same idea. Okay. Yeah, if I ask p-value, then you can't really do anything. Then you have to give. Well, you tell if this you can write if this less than 5%, then you. Hmm? Yeah, yeah. If I ask a p-value, just give me Excel formula, then you're done. Okay. But that means that I'm not very likely I'll ask, but if I ask, then you'll be like that. Okay. Yeah, just give me the Excel formula, then you're done. Okay. I think if I ask p-value, of course, right? There's no way you can do anything, right? I mean, no way except normal, maybe you can do it, but for the T, you really can't do it. Okay. Basically, you do based on critical value method for the T, right? Yeah, yeah, yeah. But I would just wait to save time. You can just do one, right? But of course, you can do both if you want to be safe. Um, in the exam, you better bring your own table. But I think for the T, we have some value that is given to you. For the F, I think you have to rely on the Excel because you can't bring all the tables in, right? Because there are too many numbers you can bring. But for the F, probably you have to rely on the Excel. Okay, probably you know how to use Excel function to do your job. Okay, but other than that, should be fine. And if standard normal, then the Z, then you can basically use the table you have, right? So that's not a big issue there. But it's open book, so you bring whatever you need. That's fine. Okay. Uh, but I think the thing is like the safe bet. Maybe you want to bring the table I already give here. That would at least in the slide or the Z table you're there, or you can also bring the T table. Should be okay. Okay. I think that will be sufficient. I guess. Okay. Should be. Yep. Everyone knows Friday. Um, Sunny and windy. Regression. Yeah. Yeah. Failed to reject. That's true. Bye 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 bye. WHMY 505. Yes, that's good. This is our last time we're here. The lecture speed is okay. Um, More or less you can follow. Um, oh, I have a hero here who is very happy, not very super, not tired. Oh, if not study this, I think it's not that easy because we hold egg is not that easy to do it. But I think it's okay. I think if you from this class, but the problem is in this class we don't have enough math. So if you really want to do that, then you have to go through the technical part to know all the math before you really go to the stat department. Otherwise, you don't know how to do the proof because in stat department they actually do proofs. Okay, how to manipulate the thing, which not recover. Okay, you have to know calculus. If you have calculus background, maybe okay, but if you don't have calculus background, there's a problem because the continuous random variable we omit all those things, right? If you don't do all the proofs. Well, thank you very much. We'll miss you, I guess, as well. So where we let's continue our journey, right? The slope. Okay. Uh, so the same idea here, we can derive the variance of B equal to this formula, right? And you can imagine the numerator is obvious, right? If more the underlying data is more variation, the slope you got has more variation. And the denominator actually said also if your data is a lot of data far away from mean, of course, B is also far away. But let me draw a picture to kind of convince you this is true. So you can compare these two cases. This is the data generating process. Y equal to A plus BX. Alpha plus beta X. Okay. And if your data is somewhere here, here. Okay. As compared to here. No, I can't do that. Sorry. I can only do that because I have to make the constant variances. Okay. You will see if you run this regression, depending on what data you get, suppose this is data. Okay. Your regression line look like this. Right. And can be look like this as well. But with this one, it will look like, it can look like this, right? It can also look like that. Okay. So you will see this has less steep, right? Compared to this guy. This guy are much more flip, right? The slope is more variation. In this case, right, the data are more concentrated to the center of X. This one is more spread out. Okay. The more spread out would have the slope is not so different. So it's inversely related. Okay. So this is the formula. And again, B is also a bell curve. You're willing to assume it's on bell curve, and then you can replace by SB. So that's the same idea goes on here, right? So again, the main idea is the same, right? So this is the B, right? Center the beta. And this will be sigma square B, right? But this is not known, so we will use SB, right? To do the job, right? So we're trying to see the B you got is far away enough from beta or not, right? Is either is we're close or we're far away, right? The problem is it close and far enough, right? Then the way to do it is look at how many is SD from the mean, right? From 0, what we usually do, right? And that's why with B minus the proposed mean, but this is 0, so that's B over SB. And you check the T table n minus 2. Okay. And we know how to do that, right? And this complicated formula, we're not going to work on it because Excel output all this, the same idea, B plus minus this value times SB, right? We know that. Okay. And just to remind you what are days, is actually in this particular slide, right? Is actually here, right? This is what we say, this is B, right? This is S of B, and this is simply B over S of B, right? And this is the P value, right? The P value comes from this, right? Tn minus 2 here. This is 0. This is the T, right? And it's actually this area times 2, okay? And to be exact, well, this area, this T is 1.9, so you can check. This is actually 1 minus T this 1.059. The degree of freedom is n minus 2, n is 5 here, so it's 3, and true. Okay, so you can calculate this, you can check, will be this number. Okay, and you can also calculate the confidence interval, right? This one, right? This 2 is just simply B plus minus Tn minus 1 alpha over 2, right? S of B. Okay. S of B is here. B is here, but what's this guy? This guy you should know already, right? 95%, so there will be T inverse 0.975 3. Okay, so you can check. You should check as well at home whether this number plus minus this number times 0.66 is actually this two number. You can check. Okay, and you should check, right? Because you don't believe everything I said, right? You should do everything with cautious, right? That's like AI, right? AI, true 99% of time, right? 1% is wrong, right? Same as what I said, right? I cannot, for sure that I cannot make sure that 100% I say is correct, right? But I think I'm 90, I mean, I'm probably better than AI a little bit, but because I teach this many times, so you should be better than AI, maybe 99.5. But you should be careful checking everything. Yes. Why? Because n is degree of freedom is n minus 2. Because you, the simplest idea is because you estimate A and B, so you lost 2 degree of freedom. So basically the idea is depend on how many parameters you estimate, then you will subtract that from n. So that's why it's n minus 2. But of course, that is a shortcut. But of course, you have to prove it by math, but we don't do the math. But the simple idea is if you estimate 2, then that's why math 2. But if you say you estimate more, you go to next 202 on, you estimate, say, 5 in the 5 variable, then you use n minus 5. Okay, you estimate 6, then you n minus 6. Okay, but in our class, it's always n minus 2. Okay, n is here in case you don't see the data. Okay, so if there's no question, then let me quickly that's okay. Let me quickly talk about the R square. Okay, and R square actually talk about ANOVA, but R square we define as SSR over SST. But what is SSR and SST? Okay. Let's look at the formula because it's easier to look at this picture. Okay. So the green dots are your data, and the black line is your regression line. Okay. So SST will be just your number minus the bar, right? So that's basically this guy. What is it capturing? This is capturing the sum of the total. It's the total variation from data, right? Because this is the part that actually you want to explain by your model, right? Because if your model is useless, how you predict y? Simply y bar, right? Y bar is the model if you x is ridiculous, right? If x is not useful, the dashed line is your model, right? The dashed line model. So the thing is explained by your model needed to be is SST. Okay. And you would ask, what is explained by your model, the derivation by your model, is SSR, which is sum of, look at this y hat minus y bar square. Okay. This is the part that we call sum of square regression. It's the part that the variation that explained it by the regression, right? So you want to explain this, the model tell you that, okay, if your x is away from x bar, that is my explanation, right? So what explained it in your model is you tell the people, okay, your x is away from x bar like this, so that's why you increase your y like this, okay? So that is the idea, okay? You explain why y is different from y bar because x is different from x bar. And you explain it by this line. So this is called the SSR. This is called the sum of square regression. And the last one, this is SSE. If you notice, this is our old friend. This is something we try to minimize all the time, right? It's the line and the point, the vertical distance, okay? And this is our old friend. We know how to write that down, right? It's y minus y hat, right? The line, right? And this is the thing that we try to minimize. It's the thing that is not yet explained by your model, okay? So to evaluate the performance of the model, okay, we can look at this ratio R square is as SST as denominator and SSR as numerator, okay? So this will capture the idea that how much variation we want to explain, that is explained by your regression, okay? And why this is a good measure, one thing that we don't have time to show, but you will see the same from ANOVA, is we have this formula, which is evident from the model, okay? Looks like the blue part is same as the deep red, the light red plus the deep red, right? The SST used to be equal to SSR plus SSE, okay? That means that if this equation holds, this must be less than this, right? So this means that the R square must be between 1 and 0. Okay. And the good thing about this is if 0, that means what? SSR is 0, right? Which means that your model is actually a flat line, right? Y hat is same as the Y bar, right? What if this is R square is 1? R square is 1 means SSE is 0. If SSE is 0 means every dot is on the line. Perfect fit. So that what we have is 1 is perfect fit, 0, the lousy fit. Okay? So that means that that's the best thing you can imagine to have. If SSE is 0, then every dot is on the line, on the Y hat, right? So that means that this is a perfect fit, right? Because SSR equals SST, right? The thing you want to explain is actually fully explained by your model. Okay? If SSR is 0, right? Which means that the Y hat, the line is same as the flat Y bar. So complete your model is useless, right? Because that means that the slope is 0. Okay? And that means that we have a useless model. So 1 is the most fit, 0 is the most not fit. So R squared, that's why it's called coefficient of determination, is the percentage of variance of Y explained by the variance of X. Okay, that is the definition. Okay, let me repeat. R squared is the percentage of variation of Y explained by variation of X. Okay, and it must be between 0 to 1. Okay, and this R squared is indeed in your Excel output, which I point out later. Okay, it's there for you to see. I think in this regression it's 27. Okay, percent. Okay, is that okay for R square? So there's a minor fact here, also very interesting. Why we choose big R square here? In fact, that go back to topic 1. If you remember topic 1, we learned the last measure is called correlation coefficient. Remember that. And actually, correlation coefficient, we call small r. And in this particular case, only true in the simple linear regression. And this R square is same as R square is the correlation coefficient square, same. Okay. Turn out to be very interestingly. But remember, this is only true when you have simple linear regression. When you go to 2021, you have more X, then it doesn't work. Okay. So it doesn't work, only work for this simple environment. Okay. But in any case, okay. Is that okay? Okay. It is R square. So one thing that when we talk about ANOVA, then you should have F test to be seen, right? So you expect some F test to be seen. So did I mention that when SSR is close to 0, then you expect the line is actually flat, right? Actually, beta is 0. So actually, we'll use this fact to go on to say if this guy is close to 0 or very small, then we can use it to test our beta is 0 or not. Okay? So let me define that formally here. So we're done with R square. So the next concept we're going to do is we call the mean square error and MSE. Okay. So this one we know very well, right? Mean square error is estimating S square, right? S square is what is estimating this guy, right? The variation of the error term, right? So what is this YSSR over 1? What is it doing? Okay. This is also measuring sigma square. Okay. But with something related to beta. Okay. And particular, if beta equal to 0, is only the MSR only reflecting sigma square. You can imagine, look at the graph again. Okay. If actually beta is 0, the regression line is flat. Okay. So the MSR, which is a measuring also will have a element of the sigma, right? And it should be the same, right? So the idea is like this, same as here. You compare variance based on this object and this object, right? This is very similar to sum of square within. This is like SSG. Okay. And remember, when the ANOVA, you compare what? The F test is compare right? You're asking, sorry, MSG. Sorry. This is the ANOVA, right? If you remember what we do in the previous chapter, you compare the variance calculated based on between group and within group, right? If there's a lot of different between group and within group, right? We'll reject, right? Same idea here. We'll do the same idea if you calculate the variance based on this, okay? If this is much bigger than this one, right? That means that the beta will not be 0. Okay, so the same idea. So we'll compare MSR over MSG. Okay, so MSE, sorry. The main idea is that MSE is always the good measure for sigma squared, then no problem. But MSR, if beta is not 0, you contain the effect of beta, right? You'll be bigger, right? Because it's affecting how you run the regression, right? So that means that it's again, it's a right tail test. Okay. It will be, right? You will check because the equilibrium 1, so you will check F1 and n minus 2. Okay, so you check this table. So this F test is testing what? Testing beta equal to 0 and beta not. Okay, you will say, wait a minute, did we do that in T test? Yes, we do the T test, but we can do in this simple linear regression. T test is same as the F test, okay, on beta. And you ask why we do that? Because when you have more than one variable regression, then the F test and T test will be different, right? Because F test is at the same time testing everything is 0, 0 or not. Okay, holistic approach. Okay, the same as you learn ANOVA, you compare the group mean, right? Many groups. You can also do the T test for each group, right? I mean, that's the same thing. But one F test is much faster. Okay, so let me go to the Excel, which is the most important part, right? So as you can see, right, as we have said, this is our SSR, and this is our SSE, and this is our SST. So you can see SSR plus SSE is equal to SST, right? And second, if you divide SSR over SST, you get R square, right? This is SSR over SST, right? This is R square. And the first thing you can see here, this is 1. There's no, because you only have one intercept, it's 1. This is n minus 2, right? N is 5 here. And this is MSR, right? MSR is SSR over 1, so the same thing. And this is what? MSE, right? Is SSE and over 2. And this guy is what? Is F is MSR over MSE. Okay. And once you did that, you do F test. It's a one-tail F test, right? So that is 1 minus. So we basically explain everything here, right? So there's nothing, we leave no stone unturned. So almost everything except multiple R and adjust R square, which is not covered in this class. Almost everything you would know how to understand, right? Almost everything, there's nothing you don't know from this diagram. And this is S, right? So everything is explained in this Excel. So I hope you were able to understand this Excel. Okay, that would be a good one. Is that okay? Is that okay? Any question? I think that's the most single important slide in this class. Same as ANOVA, right? You would be knowing every single aspect of this line, how this formula to calculate, what the meaning of them. You know that, I think my job is over, right? Because that is what you need, right? You look at data, you run this Excel, right? Add in, you're done, right? I think I run the add in before, right? This class. Okay. So that's 5 minutes. I'll cover one slide and we're over. It's just one slide more. Any question? Any more question? I mean, I have one slide to cover. Another question? If no, then I'm done. There's one last slide that will conclude my class. Or one or two more slides. So it will be this slide. Okay. So someone asked me what's x0. Okay. So before I do that, just add a graph, then almost done. Okay. So bear with me. Just 5 minutes. I think we are okay. So remember our goal. We have x and y. We have many data point here. Okay. And once we run this regression, we got the line. We're happy. Okay. Excel gives us line. And then we look at this A and this B, right? And we've done hypothesis testing on A and B, happy, right? If you can reject it from 0, right? The p-value is small enough, then you are done, right? You are very happy. You render this regression very nice, right? Everything is nice, this model, right? And this line we have, right? We have the line, so-called y hat equal to a plus bx, right? You reject the null that alpha equal to 0, then you're gone. You also do that beta equals 0 are gone. Then this model is useful by itself. Okay. So now the very next step is this line represent what? This line is only a point estimate, right? It's only a point estimate, right? So it's good if you give me a particular x0 number here, go up, right? This y hat will be a plus bx0. Okay. So this is our point estimate, right? But we are not just happy with point estimate, right? We want to know any 95% confidence of this number, right? Because we know not just x determining the y, but also epsilon. So we want to know 95% of time where it is. Okay, that's a question. Okay, that is called the confidence interval. Okay, and the formula to be used, we need to know, okay, the variance of this guy, right? We know the variance of this, right? Or what we call the variance of this a plus bx0, right? If we know that, we know it's normal, we can, or t, right? We can use the idea, right? If you know the variation, then you can tell you that 95% where they are, right? Just like the typhoon, the observatory tell you the location, but also tell you where it is, right? So turn out the formula like this. Okay, suppose the variance is like this crazy formula. Okay, and the standard error will come with this formula. Okay, and that's why you can do this t plus the standard error. Okay, so that's why this example will demonstrate all the calculation. You can calculate that. Okay, and if you, this is the calculation. I'm not going to go into detail because if you learn advanced class, if you have a software, this can be calculated directly. Okay, so that's why I'm not interested in that. But I want to tell you a lasting thing is you will see if you try to draw the confidence interval, something will happen like this. Okay, this is very narrow here, and this is very wide. Okay, and it's narrow when it is near x bar. Okay, the more closer to x bar, you'll be, the variance is very small. The further away from X bar, the variance is large. Why it's true? Actually, this is in the equation. Look at the equation again. If your prediction is far away from X bar, this variance is large. Okay. And just give an analog, our last analog is like this. Sorry for 1 minute overrun, but if you look at the map, well, this is Hong Kong, Hainan Island, Taiwan, there's some Japan, and there's some Philippines, right? And the typhoon come in this way, right? And you will see if typhoon is here, observatory will also give you this 95 confidence, okay? And you will see the confidence is getting larger and larger when it's away from today, right? The thing expand, okay? Same idea here. We have very good knowledge when the data is nearby X bar, right? But if you're far away from X bar, we're less confident. So the confidence actually will expand. So when you run regression, the regression model will be very good near X bar, right? If you're away from X bar, your interval is larger. So you have less confidence about your regression. Okay. So the regression line, although it's straight line, it doesn't mean everywhere is very good as others. Okay. It's the best near the mean. Away from the mean further, your regression has less confidence. Okay. So that's what I want to say. So that's all for our course. And then next Wednesday, we'll go over the past paper and Q&A. So please try to do before you come to the class. Okay. No more from me. So that's end. And good luck for the weekend and the exam next week.